All right, so in this video, we're going to look at some other notations for how we can write derivatives. And we're going to look at how we can calculate the actual numerical values of derivatives at specific points. And then we're going to look at the situations in which derivatives can fail to exist. All right, so there's going to be several ways which you can represent derivatives, and you're going to need to be familiar with more than a couple, because when you're representing derivatives in different scenarios involving different types of functions, especially in physics, it can be confusing if you don't get the notation down. All right, so the basic way that's really common is when you say f prime of x. So it's basically like f with like apostrophe and parentheses with the x inside. Simple way is when we say y prime, you just write it like that. However, this way is gotta be careful because it doesn't specify what the independent variable is. And we're gonna learn later on that the independent variable doesn't always have to be x. It could be t or whatever, depending on the scenario. Now this is gonna be the way which we write it, like in terms of looking at it in like a ratio or a fraction. So the derivative of y with respect to x, we usually will write it like dy over dx. And then derivative of f of x with respect to x. So you can write this as d of f of x. Usually I'll put it in brackets of all over dx. So become familiar with all of them. Again, it just takes practice when you first start doing calculations with derivatives. It's going to catch on pretty easily. All right, now for this problem, we're going to find the derivative value. So we're going to get some number, if possible, at the points where x is 0, 1, and 4 on this graph for the function f of x equals the square root of x. So let's actually just first draw a sketch of this graph through those points. So we know it goes through 0, 0, 1, 1, 4, 2. Well, as we should know, it's a common square root function. So something like that. Okay, so now let's go through the limit process for calculating the derivative. So again, let's find a general equation. So f prime of x will be equal to the limit as delta x goes to 0. Remember, of f of x plus delta x. And let's go ahead, let's just jump one step ahead because we should be familiar with that. So remember, f of x plus delta x. So since f of x is the square root of x, what we're going to have in this first part is the square root of x plus delta x minus f of x, which will just be the square root of x. So that's what f of x is defined as, all over delta x. Now, this is going to be a case where we're going to have to do some fancy, I guess like magic with how we're going to get rid of this delta x in the denominator. And then for this case, we're going to multiply by the conjugate. So what we're going to get is, let's write this over here. Putting this in brackets, I'm going to try to write it clear so we don't get it confused with what we're doing. So I'm rewriting this first one over just the expression. That's over delta x. So this is our original expression. And we're going to multiply this by fancy form of the number 1. So we want to multiply by 1 doesn't change the value, it's just going to change the way it looks. So we're going to multiply by the conjugate of this expression, which will just be, instead of minusing that square root of x there, we're going to add the square root of x to it. And we're going to keep the denominator the same because that's how we make sure that's equal to 1. Okay, now the reason we do this is because you're gonna see some stuff cancel. So what happens here is that, again, distributing the square root of x plus delta x times the square root of x plus delta x simply cancels that square root part. And let me just go right over here, actually, so not cramming. So it just becomes x plus delta x without the square root. Then we're going to do the square root of x plus delta x times the square root of x. And for that, we're just going to leave it as that, as square root of, and that's, I'm not going to do any simplifying here or any fancy, algebra, because what happens is you see it's going to cancel out with its conjugate. We're going to then multiply by the minus square root of x times the square root of x plus delta x. And so that'll be negative square root of x times x plus delta x. And then this by that last one there. So that'll just be minus x because the square root operation will cancel. Now see here, this and this are just opposites. Even though they may look a little complicated at first glance, they're going to cancel each other out. Now for the denominator, just multiply it across, but don't distribute. Just like write it in that way. So delta x times the square root of x plus delta x. Well, whoops. Plus delta x. And so what happens is the numerator becomes x plus delta x minus x. So in addition, these x's cancel, x minus x cancel, and all you have left on top is actually just a delta x. And magically, see, you have that delta x there in the denominator multiplied by that, by the rest of that. I don't know why I put it in brackets. Seems like it's making it harder, my life more difficult. The square root of x plus delta x plus square root of x. So we'll leave it like that. No, don't try to do any fancy canceling. And that's because these delta x will cancel there. And so all you're going to have left is 1 on top. So you're going to have 1 over this entire group. And so we'll have f prime of x. I should have wrote this over, but it's all right. F prime of x equals the limit as delta x goes to 0 of 1 over this. Now, see, we can now plug delta, we can now plug, 0 in for delta x, because it's not going to cause any issues. We'll just have the square root of x plus 0, which is the square root of x, plus 0. And that's all good, because we're not going to have like any undefined, expression left. So this will just be equal to 1 over the square root of x plus 0 plus 0. So it should be 1 over the square root of x. Oh, whoops, sorry, not. This one is actually not 0, that's just plus the delta x. My bad. So what you actually have is 2 delta x, or 2, sorry, not, you have the square root of x here. So what you have is 1 over 2 times the square root of x. So 1 over 2 root x will be your final equation for the derivative of f of x. Now, remember, this is a function that describes the derivative. So to find the actual value of the derivative at these points, you're just going to plug in those x values. We're going to plug in 0, 1, and 4, and then just calculate. So for the first one, if you want to find f prime of 0, that'll be 1 over 2 times 0, which is actually going to be undefined. Or 1 over 2 times the square root of 0. Undefined. We'll talk about what that means in just a minute. Now I want to look at what f prime of 1 is. So f prime of 1 will just be equal to 1 over 2 times the square root of 1, or 1 over 2. So just 1/2. And then f prime of 4. One over 2 times the square root of 4. So 1 over 2 times 2, which will just be 1/4. Okay, so let's, what is it? Let's represent. Let's write, or let's show what these values mean. So it's similar to the tangent line problems we were doing before, except we're just calculating the value of the slope. So this doesn't tell you the equation of the tangent line, but it still gives you an idea of what's going on. So at x is 0, what you have is a vertical tangent line, because that describes a line that has an undefined slope. So let me actually write that down. Vertical tangent. Now, when x is 1, there's a slope of 1/2. So at this point, you can write, there we can show the tangent line would be something like this. At 1, 1, let's write that 1, 1. And then at 2, 4, the slope of the tangent line is 1/4. So it'd be much more steep, it would be going, if you want to get really more precise, we would run it like all the way across like that. F prime is 1/4. So let's always make sure to not lose, our understanding of the concept behind derivative when we're going through the calculations. All right, now let's look at some situations where a function can fail to have a derivative, so where it's not differentiable. So you kind of already had one example, like over here. See, we had a vertical tangent line, at 0. So that's one of our general cases where the derivative is undefined, or we say where the derivative fails to exist. So an example of one could maybe be our cube root graph, where we have like a graph maybe does something like this. Well, what's that? So you have a vertical tangent line here. Vertical tangent line. Another case is where we have some sort of like sharp point where like the two sides of a function collide, or make a like a weird sharp cusp. So we say not smooth. It's not smoothly connected. So let's say we have maybe a graph that does like something like this. This would be our graph of f. So there's like a, something where we're going on in the derivative here, because from the left side, the derivative would be, something like that. But from the right side, the derivative would be sloping like that. See, so the problem is that the derivative is not equivalent when you approach this graph from the right and from the left. So even though the graph of the function is continuous at that point, the right hand and left hand, slopes, aren't equal. So the function fails to be differentiable here. We like to kind of think this is like a sharp point. That's how I usually will explain to my students. So left hand and right hand. Slopes aren't equal. Point that thing. All right, and a third general case is probably one of the most obvious. It's where you have a point of discontinuity. So where's the jump or the point, or the graph is broken. So maybe the graph does something like this, and then continues this way or something. We have discontinuity here. Discontinuity. All right, I put the word in there.